Hello, today I'll be talking about creating a high-resolution CT template. We will touch on the methods creating the template as well as its applications in deep learning. So a CT is created by an X-ray beam that goes around an object, in this case a human, in a circle. A detector on the other side measures how many X-rays get through, and from that the density of the object can be assessed. On the right-hand side, we show a head CT of someone with a hemorrhagic stroke on a grayscale image. You see the skull is bright, as well as additional areas other than the human, such as the table. If you changed the contrast settings, you'd also see the pillow the person was laying their head on. This density from a CT is commonly measured in Hounsfield units, or Who, named after Sir Godfrey Hounsfield. They are relatively standardized, where if you were scanned in two different scanners, they'd be close in absolute value of the units. The values are standardized to the density of air and water. Values of water are around 0, and value of air are around -1000 or sometimes -1024. The brain and tissue falls within 0 to 100 in CT where contrast agents haven't been delivered. So what do we mean by a template? The most popular is the MNI template from the Montreal Neurological Institute for Magnetic Resonance Imaging. It's a population average of a number of participants, and usually defines a reference space. That space is important because labeled atlases have indicators for which structures are at which locations. In 2018, there was a study of over 300,000 head CT scans from India. The group released an open subset of the data called the CQ500. If we look a bit on the release, there is information on the licenses. The data is licensed under a Creative Commons Attribution Non-Commercial Share-alike license, which means we can share the data and build upon this data as long as we give credit to the authors, use it for non-commercial purposes, and distribute our work under the same license as the original. The released data is 491 scanning sessions from clinical data, which includes patients with pathology, like hematomas or brain bleeds, physical distortions of the brain due to a number of reasons, and breaks, namely skull fractures. We want a healthy template as much as possible from this data, so we first subset the data to the 222 who had no indication of pathology. Of that, 130 subjects had a high-resolution scan, which we defined as having a z-axis resolution of 0.7 mm or less, as well as a thick slice scan, which is commonly 5 mm in the z-axis. We chose a scan with the closest resolution to 0.5 mm³ as a baseline starting template. It was resampled to 0.5 mm³ so that the voxels, aka 3D pixels, were isotropic, the same size. We will show how after this initialization, an average of the population is used as the template. Some of the main downsides of the CQ500 compared to other templates is that no clinical or demographic information is presented with the data, which limits generalizability of the template. The population, to our knowledge, are exclusively from India, and it's unclear the number of sites the patients came from. We may connect with the group for a collaboration, as they have the information. Here is the main crux of the work. We have the 130 skull stripped images from different subjects. Overall, this is a gradient descent procedure to estimate the average brain. We register each brain image to the initial template using symmetric normalization or SYN from ANTSR, which outputs a transformation map, called G sub I, and registered image for each subject. We average all the registered scans, voxel-wise, to get a population average map. We then average the transformations and multiply that by a gradient step, in this case -0.2, then apply that to the average image to get a new template for the next iteration. This process is repeated over and over to get the final template. But how do we know if the algorithm converged or is done? We need some stopping criteria. We use two measures, the dice similarity coefficient and root mean squared error or RMSE. We thresholded the template for values greater than 0 to get a template mask. We then compared this mask to the one from the previous iteration to get a dice score, which measures overlap. A value of 0 indicates no overlap, and 1 indicates perfect overlap. This allows us to estimate how the shape of the brain and brain surface are changing with each iteration. The RMSE was calculated by taking the difference of each template, voxel-wise, squaring that difference, and then taking the average, then giving a square root. As CT scans are usually measured in integers, we would ideally like a RMSE of less than 1, but the lower the RMSE the better, and we achieve results less than 2. We performed 40 iterations of the algorithm, as it is very computationally intensive. On the left panel, we see the dice score as the iterations increase. After iteration 15 or so, we see a very high dice score, indicating not much change to the total brain area, achieving the highest dice around iteration 20. Looking at the RMSE, we see a similar pattern, with a steady drop until iteration 18 or so and then a lowest point at iteration 37, which we chose as it had the lowest RMSE and a high dice overlap. Here is the resulting template from iteration 37, which was the final template released. We can see it is overall smooth, with the ability to see deep gray matter structures such as the putamen, but with clearly less contrast than an MRI. We also took the voxel-wise standard deviation image, which shows some potential falx cerebri calcifications, causing a high degree of variability around the midline. This image can be useful in creating features for machine learning, as well as indicate which areas are most variable when registering to this template. All of this was done in R and relies heavily on the ANTSR package. The code for this is located on the provided link for the GitHub, including the final templates presented in the previous slides. Now we have the template, we have a population level space. This is good enough on its own for doing population-level analyses and putting patient scans in the same space, but many times anatomical labels are of interest. We used 35 labeled MRI scans from the MICCAI 2012 Grand Challenge, which had over 180 individual structures segmented for each scan. We performed label fusion on these atlases by registering each brain MRI scan to our template using SYN, and applying the estimated transformation to the labeled structure map, as well as the tissue class segmentation of white matter, gray matter, and cerebrospinal fluid. We averaged these labels using Staple to get the structure map and the tissue class map. To get just the ventricles, we performed a two-class segmentation using Atropos from ANTSR to get a segmentation of cerebrospinal fluid versus the brain, and then applied the Alvin ventricle mask to that to get an estimate of the lateral ventricles in the template. Here we see the estimated structures from the label fusion approach. These labels may be imperfect, but may be a good start for a coarse analysis. We additionally performed label fusion on the tissue class maps, providing a tissue class map for the template, seen in panel B. We masked the lateral ventricles, which may be of interest in analysis. We padded the Z direction to 512 slices to make the template a cube. Most CT scans have axial slices of 512 by 512, so this integrates easily with this data. Also, as a cube, and a multiple of 8, it aligns well with the needs of deep learning models, notably convolutional neural networks and the TensorFlow framework. If is easily downsampled to other dimensions, remaining as an isotropic cube, which is important as some GPU memory restrictions may need smaller images. As CQ500, it is released under the same license. Thanks for your time. If you know anyone working in CT imaging, please send them the link to the template and the associated paper. Also have them reach out to me if they want.